Efficient certification and the definition of MP. Reducibility among problems was the first main ingredient in our study of computational intractability. The second ingredient is a characterization of the class of problems that we are dealing with. Combining these two ingredients together with a powerful theorem of Cook and Levin will yield some surprising consequences. Recall that in Chapter 1, when we first encountered the independent set problem, we asked, can we say anything good about it from a computational point of view? And indeed, there was something. If a graph does contain an independent set of size at least k, then we would give you an easy proof of this fact by exhibiting such an independent set. Similarly, if a three-set instance is satisfiable, we can prove this to you by revealing the satisfying assignment. It may be an enormously difficult task to actually find such an assignment, but if we've done the hard work of finding one, it's easy for you to plug it into the closest and check that they are all satisfied. The issue here is the contrast between finding a solution and checking
for
a
independent set or three set. We
for
do not know a polynomial time algorithm to find solutions.
We do not
but checking a proposed solution to these problems can be easily done in polynomial time.
Checking a
to see
proposed
that
solution
this
to
is not
these
an
problems
entirely
can be
trivial
easily done
issue.
in polynomial
Consider
time.
the problem
To
with
see
face
that this
if
is
we
not
had to
an
prove
entirely
that a
trivial
three-set
issue.
instance was
Consider
not
the problem
satisfiable.
with face
What
if
evidence
we had
could we
to
show
prove
that
a
would convince
three-set
you
instance
in polynomial
was
time
not
that the instance was
satisfiable?
unsatisfiable? Problems and algorithms. This will be the crux of our characterization. We now proceed to formalize it. The input to a computational problem will be encoded as a finite binary string S. We denote the length of a string S by the size of S. We will identify a decision problem X with the set of strings on which the answer is yes. An algorithm A for a decision problem receives an input string S and returns the value yes or no. We will denote this returned value by A of S. We say that A solves the problem X if for all strings S, we have A of S equals to yes if and only if S is in X. As always, we say that A has a polynomial running time if there is a polynomial function p dot, so that for every input string S, the algorithm A terminates on S in at most big O of p of the size of S steps. Thus far in the book, we have been concerned with problems solvable in polynomial time. In the notation above, we can express this as the set P of all problems X for which there exists an algorithm A with a polynomial running time that solves X. Efficient certification. Now, how should we formalize the idea that a solution to a problem can be checked efficiently independently of whether it can be solved efficiently? A checking algorithm for a problem X has a different structure from an algorithm that actually seeks to solve the problem. In order to check a solution, we need the input string S as well as a separate certificate string T that contains the evidence that S is a yes instance of X. Thus, we say that B is an efficient certifier for a problem X if the following properties hold. B is a polynomial time algorithm that takes two input arguments, S and T. There is a polynomial function P, so that for every string S, we have S in X if and only if there exists a string T such that the size of T is less than or equals to P of the size of S and B of ST is equals to yes. It takes some time to really think through what this definition is saying. One should view an efficient certifier as approaching a problem X from a manually try to decide whether an input S belongs to X on its own, whether it is willing to efficiently evaluate proposed proofs T that S belongs to X, provided that they are not too long and it is a correct algorithm in the weak sense that S belongs to X, if and only if there exists a proof that will convince it. An efficient certifier B can be used as the core component of a brute force algorithm for a problem X. On an input S, try all strings T of length which is less than or equals to P of the size of S, and see if B of ST is equal to yes for any of these strings. But the existence of B does not provide us with any clear way to decide an efficient algorithm that actually solves X. After all, it is still up to us to find a string T that will cause B of ST to say yes, and there are exponentially many possibilities for T. NP, a class of problems. We define NP to be the set of all problems for which there exists an efficient certifier. Here is one thing we can observe immediately. 8.10. P, which is a subset or equals to NP. Proof: consider a problem X is in P. This means that there is a polynomial time algorithm A that solves X. To show that X is in NP, we must show that there is an efficient certifier B for X. This is very easy. We design B as follows. When presented with the input pair ST, the certifier B simply returns the value A of S. Think of B as a very hands-on manager that ignores the proposed proof T and simply solves the problem on its own. Why is B an efficient certifier for X? Clearly, it has polynomial running time, since A does. If a string S, which is in X, then for every T of length at most P of the size of S, we have B of ST is equals to yes. On the other hand, if S is not in X, then for every T of length at most P of the size of S, we have B of ST is equals to no. We can easily check that the problems introduced in the first two sections belong to NP. It is a matter of determining how an efficient certifier for each of them will make use of a certificate string T. For example, for the 3 satisfiability problem, the certificate T is an assignment of truth values to the variables. The certifier B evaluates the given set of clauses with respect to this assignment. For the independent set problem, the certificate T is the identity of a set of at least k vertices. The certifier B checks that for these vertices, no edge joins any pair of them. For the set cover problem, the certificate T is a list of k sets from the given collection. The certifier checks that the union of these sets is equal to the underlying set U. Yet, we cannot prove that any of these problems require more than polynomial time to solve. Indeed, we cannot prove that there is any problem in NP that does not belong to P. So, in place of a concrete theorem, we can only ask a question. 8.11. Is there a problem in NP that does not belong to P? Does P equals to NP? The question of whether P is equals to NP is the fundamental in the area of algorithms, and it is one of the most famous problems in computer science. The general belief is that they are not equal, and this is taken as a working hypothesis throughout the field, but there is not a lot of hard technical evidence for it. It is more based on the sense that P is equals to NP would be too amazing to be true. How could there be a general transformation from the task of checking a solution to the much harder task of actually finding a solution? How could there be a general means for designing efficient algorithms, powerful enough to handle all these hard problems that we have somehow failed to discover? More generally, a huge amount of effort has gone into failed attempts at designing polynomial time algorithms for hard problems in NP. Perhaps the most natural explanation for this consistent failure is that these problems simply cannot be solved in polynomial time.